Hello again, everybody. Welcome to a new screencast lecture. Tonight's topic is physical changes. Let's get started. Before we do anything, though, I must point out that I have this pretty lit flat brim hat that was given to me for buying the new baseball game, the show 2018. Not sponsored by them, but we should be. So you guys at EA Sports, give us a buzz. Now, before we do anything, it's probably a good idea to do a quick review on physical properties before we do anything about physical changes. So let's take a look at physical properties. First of all, the definition of physical properties, you should already know. This is the characteristic that you can observe without changing or trying to change the composition of the substance. Some examples could be like hardness. We know that diamonds are the hardest material. We can scratch the diamond, but when you scratch scratch the diamond or try to scratch the diamond, you're not changing what the diamond is. It started with a diamond and then it ends up being a diamond with a scratch on it. So that's not changing what the diamond is. Another physical property could be color. Like, for example, you take a look at this. It's salt. With all the light going through it, it looks like it's white. It's a crystalline structure. So those would be examples of physical properties. Here's a more exhaustive list. Take a look at these. Make sure you know what all of them are. Now let's get started on new material. What is a physical change? The definition of physical change is that the form or appearance of the matter changes, but not its composition. In other words, in plain English, it's the stuff, it looks different, however, it's still the same stuff. A good example of this would be if you take a glass and you break it. It certainly looks different. This is a glass, this is broken glass. Certainly looks different, but it's still glass. It hasn't changed what the actual substance is. Here's a clip. Changes in state is a very common example of a physical change, and you should be able to think of the three common states of matter that we know about. Of course, solid, liquid, and gas. Those physical changes going from solid, liquid to gas, those are all physical changes. For example, if you have a block of ice, ice is water in solid form, and then if we melt that block of ice, we had water in solid form, we now have water in liquid form. It certainly looks different, certainly acts different. However, it's still water. Water in solid form, water in liquid form. Same stuff. So the ice melts, and now we have a puddle of water. If you look at water on a molecular level, it's H2O. Whether it be ice in solid form or liquid form, it's still H2O. This is a water molecule. Go ahead and draw a quick sketch of that. To me, it kind of looks like Mickey Mouse. That's the way I remembered it. Frozen water is water. Liquid water is water. They are the same substance, even though they look different and have some different properties. Dissolving. Dissolving is another good example of a physical change. This is one that's often confused because it is a little bit confusing in what dissolving is. You have particles in one substance get spread out and mixed together inside of another. This is also known as solubility. When you dissolve salt into water, it looks like the salt disappears. So you take clear water, you put salt in it, mix it up, and it becomes clear again. However, now that water is going to taste salty. Salt as a solid tastes salty. Salt dissolved in a liquid also tastes salty. And if you take a look at it on a molecular level, what you see is these molecules. You should know what these are. They look like Mickey Mouse, so we can guess that those are water. Very good. And sodium is sodium chloride, and what's going to happen is it is going to dissolve, and you're going to end up with something like this. So the sodium chloride is an ionic bond. You don't need to know about that, but it's ionized, and so the positive sodium side and the negative chlorine side is going to interact with the water molecules and dissolve. Some things that dissolve in water, here are some examples: coffee, aspirin, salt, sugar, food coloring. These are all examples of things that can dissolve in water. Real quick solubility review now. The thing that dissolves is the solute. And these are terms that we learned previously when we talked about physical properties. And the thing that solute dissolves in, that is the solvent. Very good. For salt water, then, the salt is going to be the solute, and the water is going to be the solvent. And the salt water mixture is going to be known as solution. One of the things about physical changes is physical changes often can be reversed. However, I don't really like that as a definition, because we could talk about how chemical changes, they can kind of be reversed too in some cases. And one of the other things to remember is that physical changes might be reversed, but you're not going to end up with it looking exactly the same as it did before the physical change. So if you have a block of ice and it melts, we could certainly freeze that liquid water and it'll become ice again. But if we freeze it like this, it's certainly not going to form an ice cube. It's not going to form a cube. It's going to be this roughly shaped chunk of ice down here. So physical changes can be reversed, but they're not going to look exactly like they did before. Separating mixtures through physical processes is a pretty important idea. And we can do these things in many different ways. Iron filings is something that you may be familiar with. Like, for example, one of these toys, this is something I enjoyed when I was a kid. You'd have the little magnet pen, and you can move the iron filings around and, make mustaches and beards on this guy. Iron filings, what they are is they're pieces of iron that are shaved off, almost kind of like sawdust, but with iron. Now, what about sawdust? Well, if we mix iron and sawdust together accidentally, it would be very, very difficult to go through with your fingers and pick out every single little piece of iron out of that pile of sawdust. There could be a much easier way to do that. What we want to do is think about different physical properties of iron versus physical properties of sawdust. What we would probably want to do is something special about iron. You might know that iron is magnetic. So what we could do is we could use magnetism, which will pick up the iron filings, and it's going to leave behind the in this case sand. I thought I said sawdust before, but I guess we mix it with sand. But either way, the magnet's not going to pick up the sand. It'll pick up the iron filings and leave the sand. Here's a clip.
Here we have a mixture of sand and iron, and to get this mixture unmixed, one thing we can use or take advantage of is the fact that iron is magnetic, and so I have here a magnet inside a plastic bag, and quickly pull out the iron out of the mixture. And then all we have to do is remove our magnet from the bag, or invert our bag to get the iron fully separated. Now certainly at this point there is some sand still mixed in with the iron, but we could go through a refining process where we come in here and repeat the process.
So each time get less and less sand caught up with our iron bits, and eventually we could get to the point where we have just iron in its own pile and our sand left on its own.
This is pretty neat about separating iron filings. You may have looked down your cereal. If you don't know this, before you go to bed tonight, grab a box of cereal and take a look at it. It'll probably say somewhere on the box that it's iron fortified or fortified with iron. What that means is they take iron filings and they throw it in the recipe with the cereal. So, and this is kind of neat to show. Here is something called Total Cereal. I don't believe they make this anymore, but the thing about Total Cereal is that it had a lot of iron in it, and there's ways you can pull that iron out using a very, very strong magnet. Here's a clip for you to take a look at how it's done. Here's another scenario. Let's say we have gravel and we spill milk in it. So we have a big bucket full of gravel and it's filled with milk. Now, for some reason, we want to get the milk out of it. Probably not going to want to drink it, but let's say we wanted to do that. How could we separate the milk out of a bucket of gravel versus milk? Again, think about physical properties. Now, first of all, the milk is a liquid and the gravel is a solid, and the solid is, fairly large pieces. So a good thing that we could do is we could take advantage of the difference in size of the gravel versus the fact that the milk is a liquid, and we can use filtering. Filtering is a device that's designed to physically block certain objects while letting others through depending on size. This is a coffee filter, so if you've ever seen coffee being made, water is going to be run through this, and the water is going to drip through the filter paper and come out with dissolved coffee and leave all these big chunks of coffee in the filter, because you don't really want that in your coffee cup. Here's a video clip that shows filtration. Here's something that you could use. Let's say it's an emergency situation. Let's say you are lost in the woods. You're thirsty. You find a creek, but the creek water is kind of muddy. It kind of looks kind of gross. So what you might want to do is find some sort of a cloth bag, or you might even have to use a sock. You can hang it from a tree limb like that. Pour the water into the cloth bag or sock, and the water will drip through, and some of the crud will be caught in the sock or the bag. We could use that as an emergency filter. Now, that is not going to make the water safe to drink. After you filter the water out, you're going to want to boil it, kill any beasties in there, microorganisms, and even then, that's still not going to make the water totally safe, but it'll be a lot more safe than if you just stick your face in the water and drink it straight out of the stream. Here's another scenario. We have gravel again, our good friend gravel, but this time we're going to mix in a solid, and this solid is gold. How could we separate these things? Again, think about the physical properties of gold, think about the physical properties of gravel. First of all, could we use magnetism? Magnetism is going to be good for getting out things that are made out of iron, cobalt, or nickel. If you've ever put a magnet up to a gold necklace, it should not be attracted to the magnet. If your gold necklace is attracted to a magnet, you got ripped off. It's not pure gold. So magnetism is not going to work for you. Filtering is not going to be a good choice because we don't know the sizes of the gold pieces. We don't know the sizes of the gravel. So if we use filtering, we're not going to get a good result. So we can't use filtering. We can't use magnetism. So we need to think of another physical property about gold. One of the things that that gold is really well known for is that gold has a very high what? Gold has a very high blank, which is 19.3 grams per milliliter. Gold has a very high density. That's right. Gold is very dense, and if you put gold in water and you put gravel in water at the same time and you let them go, okay, the gold is going to sink. I'm trying to do this in mirror image. The gold is going to sink much faster than the iron because gold is more dense than iron. And we can use that to our advantage to be able to separate the gold from the gravel. Here's a clip showing you about panning for gold.
Joining me today is Yukon Dan. Hello, Yukon Dan.
Hello, Dan. How are you?
I'm doing very...
I'm going to show you the art of gold panning, and within no time at all, you'll be a pro like myself.
All right, so let's get started. What are we looking at today?
Okay, first of all, we want to make sure we're holding the pan properly. We keep the riffles of the pan always away from us. This dirt is called pay dirt.
Okay.
So lots of water, shake the pay dirt side by side. The gold being extremely heavy, 19.34 times heavier than water, is going right to the bottom. I now pour out the water and slowly I wash out the sand and rock. I let the minerals go out with the water. I now stop, more water, and shake. It is extremely important that I do not put my hand in the dirt. If I do, oil from my hand can make gold float. If it floats, I lose it. So lots of water, shake, and wash. In 1858, the price of gold was $17 for an ounce. Today, $1,660 an ounce, and that's what we're
Beautiful.
all wanting, gold.
How much is there?
Each piece in here is worth a minimum 50 cents for each piece.
Okay, density can also be used to separate other mixtures. Blood is a really good example. A lot of people think that blood is just a liquid, is red liquid, but it's not. Blood is actually a mixture. It's a mixture of solids and liquids, and we can use density to separate the solid portion from the liquid portion. So if you let blood sit around long enough, we put it in a centrifuge. The centrifuge is going to spin the blood around really super fast, and it's going to be able to separate where the more dense solid portion, the red platelets and blood cells, are going to sink to the bottom, and the plasma, the liquid portion, is going to stay at the top. So here you see the liquid portion of blood, which is this plasma, is kind of this yellowish liquid, and then the more dense red portion, the platelets, blood cells, etc. Here's a clip.
Because the parts of a mixture maintain their separate identities, their physical properties can be used to separate them. Blood, for example, is a mixture of cells, plasma, and many other substances. A hematologist might want to separate out just the red blood cells from this mixture. They happen to be more dense than other components of blood, so that physical property can be put to work to make the separation. A centrifuge does it. Centrifugal force pulls the denser red blood cells out of their nearly homogeneous distribution in the mixture and concentrates them at the ends of the tubes in the centrifuge.
Anemia can indicate malnutrition first and foremost, but it can also go alongside diseases like tuberculosis and AIDS. And malaria, and so this can be used to really get people the help they need for whichever of those diseases they have.
Anemia affects over 1 billion people in the world, and something that we just really wanted to help develop and see what we could do, especially as non-engineers, to be able to make such a large impact on such a pressing need. And it was just a great challenge, and we've been working on it for so long, and excited to see the transformation this summer too.
We are so excited. We've had this in the laboratory for a whole semester now, and we are just really eager to get it out into the field and see how it can be used and how it can potentially help people.
Now that clip I think is really neat because Lila Kerr, she is a former student of ours. She's a former Family D student, and she was featured in that video clip. Pretty cool. Now let's go back to a new mixture. Now in this case I've mixed together water and sugar. So I have sugar water, and what can I do to separate the sugar out? I could take advantage of a phase change. What I could do is I could evaporate the water, or I could boil the water. That'd be a lot quicker than sitting around waiting for it to evaporate. So I'm going to vaporize the water, and after the water vaporizes, the sugar crystals are going to be left behind. Here's a clip that we can take a look at. Okay, that's really good about separating a solid that's dissolved in a liquid. Now, what if we have two liquids that are dissolved together? That could be a little trickier. For example, let's say we have mixed together water and alcohol, and there's other junk. How may we separate the alcohol out? So if you take a look at this, this is a picture from a distillery. Like if you ever go to Kentucky, it's really neat. I'm not obviously not supporting alcoholic drinking by kids, but it's a really cool tour that you can do if you go down to Kentucky, especially Lexington area. There are several different bourbon distilleries that you can tour that they're free, and it's great science. I mean, it's great chemistry that you can check out. It's actually a lot of fun, beautiful landscapes. It's a great thing to do. I strongly encourage you to do that if you get a chance to go down to the Kentucky area. How may I separate the alcohol out? What I can do is I can use phase changes. What's interesting about alcohol, in this case ethyl alcohol, it's going to boil at a much lower temperature than water does. So ethyl alcohol is going to boil at 78 degrees Celsius, and water boils at 100 degrees Celsius. So we can boil the alcohol out of the water, and that process is called distillation. When you separate two or more liquids based on different boiling points from liquids. So if you have more than one liquid dissolved in each other, we can sometimes use differences in boiling points to separate them out. And that's known as distillation. Here's a drawing of a simple distillation. What you do is you'd have the liquid that you have that you want to separate. In this case, we have water and ethanol solution. We're going to heat it up, and this is corked, and the alcohol is going to start boiling off. It's going to go into alcohol vapor here, and then this part is open. It can go into here, and this tube is sloped downwards, so gravity can pull whatever is in this tube down into this flask. Now there will be water flowing through this pipe. What this is a pipe within another tube, and this other tube has cold water in it. So when the hot water vapor hits this glass, it's going to go from a gas to a liquid, and you should know that that's called condensation, and that condensation is going to collect in this tube, and since it's sloped, eventually it's going to roll down this tube and drip out this end, and you can collect it in the glass. Here's a clip that we can take a look at of the distillation of salt water and crude oil.
Distillation makes use of that property. When a mixture contains one part that is a liquid, like the water and seawater, then we can simply boil that part away, changing it into a vapor, and then recondensing it as salt-free water. But if we repeatedly distilled tap water, we would obtain a single pure substance, water. Some substances, like crude oil, are mixtures of several liquids, and the ability of petrochemists to separate that mixture into its commercially important parts is the foundation of the multi-billion-dollar petroleum industry. Refinery can be demonstrated in the laboratory in a simplified way. The mixture of liquids in crude oil includes gasoline, the jet fuel kerosene, and diesel fuel. And all these themselves are mixtures. Each of the various mixtures boils off over a range of temperatures. In a fractionating column, the various parts of the mixture are separated. As the vapor of each part reaches the top of the column, it passes through a condenser and becomes a liquid again. The gasoline fraction condenses. The kerosene fraction. The diesel fuel fraction. And so a mixture can be separated by taking advantage of differences in the physical properties of its various parts. In our demonstration, the parts we extracted from the crude oil mixture were mixtures themselves, which could be further separated.
Here's a picture of a distillery, a distillation setup, kind of like I was discussing with you, talking about when visiting in Kentucky. And these vats, you're going to heat them up, and the alcohol is going to vaporize and go up this tube and be cooled off and can be collected as a liquid. Here's another example. It's pretty neat stuff. It's pretty cool to look at. There's a lot of local breweries, microbreweries and things like that. You can kind of see this in action as well in the area. This is an oil refinery, and this is a big column where oil, we take what's called crude oil. That crude oil is the stuff you pump out of the ground. This is black sludge that you can't really do a whole lot with, but you can boil off different portions of that crude oil and collect it and get some really good useful things. Like, for example, some of these things you probably have heard of, like gasoline, I'm sure you've heard of, kerosene, diesel fuel.
Begin to vaporize immediately. Because they're flammable, it's safer to heat the test tube with hot water, not with an open flame. As the vapor rises, it enters the sidearm where it cools and condenses, which happens at about 40 degrees Celsius. Those hydrocarbons, which boil at that temperature, drip down the sidearm and form our first fraction. It's a colorless liquid. The temperature is kept around 40 until all the hydrocarbons with this boiling point have vaporized. The remaining hydrocarbons weren't hot enough to vaporize, so their boiling points must be higher. As the temperature rises, other hydrocarbons begin to boil. The second fraction is collected at about 60 degrees Celsius. It's slightly yellow in color. By carefully heating the oil and collecting the liquids which condense at a number of different temperatures, the many different hydrocarbons in crude oil can be separated. Hot vapor rises up the fractionating column. The spiraling glass tube inside provides a condensing surface. It's a long way to go, and the further from the heat source, the cooler it gets. Most of the vapor condenses on the glass spiral and drips back into the mixture. Only the hydrocarbons, which are still vapors at the very top of the column, enter the sidearm to be condensed there into liquid. Industry uses the same process but on a mammoth scale in huge fractional distillation columns. Industrial distillation separates crude oil into useful fractions, each containing molecules of a similar size.
That's all we have for you tonight. And next time we're going to talk about chemical changes. Hope to see you then. Have a great evening and be careful, kids. Bye.